Okay, well, thank you so much for inviting me to present today. I'm excited to talk to you about a paper that was my job market paper called Delayed Inflation in Supply Chains Theory and Evidence. This is joint work with my co-author, Brian Wheaton, who's here in the audience today. And as I'm now at the Federal Reserve Board, the usual disclaimer that these views are my views and not the views of the Federal Reserve applies. Okay. So this talk really has two parts today. The first part is asking the question, how much and how quickly do commodity price movements propagate through the production network, affecting relative prices throughout the economy? And then secondly, we'll focus in on specifically the commodity of oil and ask how much and how quickly do all of these relative price movements that an oil price movement might cause ultimately affect aggregate inflation. And just going into that example a little bit, when oil prices increase, for example, we know that gas prices faced by consumers rise immediately, but so do fuel costs that firms face. So this could be, the fuel going into a tractor in agriculture. But beyond that, it also makes shipping both intermediates and final goods more expensive. And then even beyond the energy uses of oil, there's the raw material costs for production of plastics, petrochemicals, foams, asphalt, and so on. Okay, so just a roadmap for today. So on the theory side, we'll use an input-output model with Calvo pricing. So if you know the supply side setup of Elisa's paper on optimal monetary policy and networks, or the Afruzi-Badarai paper on sufficient statistics for pass-through and networks, that's the supply side we're going to think about. And then on the empirical side, we'll use various cross-industry shift share designs to make the following points, and I'll go through them in detail after summarizing. So first, network pass-through is much more gradual than you might expect, certainly more gradual than I expected going into this research. So in the case of oil, for the average industry, pass-through of a persistent price change is 60% after 1 year and 80% after 2 years. Secondly, this delay is a consequence of price rigidity interacting with the network. So there's research suggesting that price adjustment frequencies are incredibly heterogeneous across industries in the economy. But even holding that frequency constant, more downstream firms pass through the shock more gradually. And that is the case even when they're forward-looking. That's a point we'll make both in theory and in the data. Third, deviations from rational forward-lookingness can amplify this effect substantially. So that gets to the question of, are firms actually thinking about the fact that an oil price increase is gradually coming through supply chains and affecting their marginal cost? Are they anticipating that, or are they not? If they're not, the deviation can amplify the delayed pass-through substantially. And so we'll find empirically actually that network propagation of oil price movements is in line with rational expectations, but propagation for other commodities is even more gradual, suggesting substantial inattention. Fourth, then moving to the aggregation exercise, we'll find that relative price movements throughout the network due to oil actually largely pass through to aggregate inflation. And this is a statement about the United States. I should be very specific. And fifth, this pass-through explains why core inflation, which is supposedly purged of the oil component, is actually still quite forecastable using oil price movements. Okay, so there's 4 related literatures. One, that industry shocks can generate meaningful aggregate fluctuations. We'll show you that today for oil. The literature on price rigidity and networks. We're really going to dive into why it is exactly that price rigidity is amplified in networks and what that means for the transition of sectoral shocks. Third, this forward guidance puzzle in myopia. So we'll think about how to estimate myopia from observational macroeconomic data. And then finally, the empirical literature testing production network models. So now I want to get into the model, which really on the supply side, which I'll focus on today, we can do with just 3 equations. So as I mentioned, we have this kind of standard Calvo New Keynesian setup. There's going to be a continuum of firms in each sector, and each firm will have a probability of being able to change prices in each period, given by 1 minus theta I. So then at the industry level, the prices that we observe in an industry will be a function of, well, what share of firms changed prices in this period, what was their optimal price that they'll set, which I'll get into momentarily, And if they can't change prices, well, what was the price last period? Second, what is that optimal reset price? What do you set? Well, it's a weighted average of what's happened to your marginal cost today, plus what you think is going to happen to it in the future. And the key part where myopia will enter here is we're going to treat this delta, which is normally calibrated, let's say, to something like 0.96 on an annual basis. We're going to treat that as something that you could estimate. So if delta is close to 1, you're going to think a lot about movements in future marginal costs when you're setting your prices. If delta is 0, this equation will collapse to your optimal reset price, just incorporating what's happened to your marginal cost today. And then finally, what is this marginal cost equation? Well, marginal cost in a sector may fall if productivity increases. It may go up with wages according to the labor share in the sector. Importantly, this is the key term with the price of the commodity to the extent that you use the commodity directly in production. And then finally, the term where the network enters. So phi is the input-output matrix, and phi ik is the cost share in industry I of using intermediate input K. Okay, and then I already mentioned the case of delta equals 0. So note also that if prices are completely flexible, so theta equals 0, you also get that only today's marginal cost affects prices. But the difference between flexible pricing and myopia is that the first equation will still generate dynamics under myopia, whereas under flexible pricing, this equation collapses to something happening on impact as well. Okay, so now I want to go to a result that's quite well known in the literature now, but just to fix ideas. So suppose there's a one-time, fully persistent and unexpected shock to the commodity price happening in time 0. The economy was in steady state and there are no shocks to TFP. Then to a first-order approximation, we can look at the long-run equilibrium response of prices in all sectors. So that's this P infinity vector. It's going to be given by the Leontief inverse times the direct cost share in the commodity times whatever that commodity price shock was. And then a second term related to all of the general equilibrium effects that commodity price change can cause. And so I want to dive into the details on what this term in front of the commodity price is. So it can be decomposed using the well-known geometric sum formula now for the Leontief inverse into first-order effects, second-order effects, and so on. So SC is just the vector of industry's immediate direct cost shares in the commodity. So petroleum refineries, let's say, have an 80% cost share. In oil, that would just be 80% for them. Now, the second term is the input-output matrix times this SC. This is how much cost share you have indirectly in oil through your suppliers, your direct suppliers' use of oil, and then so on and so forth. You could consider the cost share inherited through your suppliers' use of oil, and so on. A prediction of the model empirically is that it doesn't matter where your network cost share comes from for your long-run pass-through. So if you have a 10% network cost share and that's all through direct use, your long-run pass-through should be the same in this model than as if all of that use was through your suppliers. And then finally, I want to mention that the immediate response of prices in this model, when theta equals 0, so pricing is flexible, is this long-run response that I'm showing you here. Okay, so now I want to get to the transition dynamics to this long run, and this is where we'll be able to get some interesting tractability, I think, in a very elegant result. So let the fraction of long-run pass-through of a fully persistent shock be given by this BIT object. So we'll just be saying that the prices in industry I at time t are some fraction BIT of their long-run target, where they're headed. And then we'll define duration of pass-through in a sector as the normal kind of definition of duration in Calvo models. And this is kind of the continuous time variant. So how does it work? Well, if you set phi I to be the rate of price adjustment, which is the continuous time variant, then this BIT object is just 1 minus e to the minus phi it, and then duration is 1 over phi. So all duration does is rank industries by their inverse rate of price adjustment. So if you have a faster rate of price adjustment, you have a lower duration. And this, again, is in a model with no network. So now I want to tell you what does duration look like in a model with a network. And this is a lot of notation, but I promise it's worth it. And it's quite nicely, I think, related to some papers in the trade literature. So we're going to turn off industry heterogeneity and the frequency of price adjustment. So theta I just equals theta for all I, and we'll use this phi again to denote the rate of price adjustment in each industry. Then I want to start with the assumption of complete myopia. So assuming firms are not forward-looking about this gradual propagation of shocks through the network, then the duration of pass-through in an industry, I claim, is going to be a cost share weighted average of your orders of exposure to the commodity. So if you only use the commodity directly in production, then this weighted average term on the slide here is going to be 1 for n equals 1. This numerator is, as we went through before, what is the cost share from a particular order of your use of the commodity. And this lower object is just your full network cost share in the commodity. So as another example, suppose 50% of your use of the commodity is through your suppliers and another 50% is through your suppliers, then this term will evaluate to 2.5 instead of 1. And so that's how this works. And the nice connection to the trade literature is this is exactly the notion of directed downstreamness that's considered in the global value chains literature, for example, in Antros and Shore and elsewhere. I want to mention, though, that it is directed, so it depends on the commodity that you've selected. Okay. Under rational expectations, we get a very similar object, but pass-through is faster. So if you're more supply chain links removed from the commodity, we're not going to be linearly increasing in those supply chain links. We're going to be roughly increasing to the square root in the number of supply chain links. And I'll give you a quite clear example of this right now. So we'll consider a linear network example, which is just a simple supply chain. In this supply chain, we have refineries using oil and labor. We have petrochemical manufacturers using refineries and labor, and so on. In a linear network, generally, sector N uses labor and inputs from sector N-1. And just applying that proposition I told you on the previous slide, the duration in sector N of pass-through is going to be N over phi. So the more supply chain links you are away from the commodity, the longer it takes pass-through to occur. Under rational expectation and a zero interest rate, duration is instead going to look like roughly the square root of N over phi. So pass-through will be faster, but it still will be slowed by downstreamness. And just to get an idea for what this looks like, I've set the frequency of price adjustment in the linear network to 0.5. And each of these lines denotes the fraction of total pass-through as we move through time. The fastest line is sector 1, then we move down to sector 2 in the linear network, and so on. Under rational expectations, you can see the gap between pass-through speeds getting smaller and smaller over time, which is where that square root of N shows up under rational expectations. Whereas if firms are completely myopic, the amount that downstreamness slows pass-through is linear in the number of supply chain links you are away from the commodity. Okay, so now I want to test some of these basic principles in reduced form empirics, and then we'll get pretty serious about the dynamics of the model and a structural estimation. Okay, so our first set of regressions tests whether network exposure to a commodity as opposed to merely direct exposure actually determines the extent of long-run pass-through in a sector. And then secondly, whether pass-through is gradual. And then finally, I explicitly want to test whether downstreamness slows pass-through even conditional on heterogeneous frequencies of price adjustment. Okay, as far as data is concerned, so from the BEA, we'll use the big input-output tables. We'll get industry prices from the BLS. The PPI series don't include agricultural prices, so we'll get those from the Department of Agriculture. The model suggests some general equilibrium wage controls that we should have in our regression, and we'll get those wages from the QCEW. Past and Schoenle and Weber very kindly offered us their measures of frequency of price adjustment by industry. So those are measures of those Calvo parameters in every industry. At times, we'll use Kanzig series of OPEC surprises that lead to changes in the oil price as an instrument for the oil price. And then finally, I want to mention our primary sample period today is 1997 onward, although when we get to aggregate inflation, we'll use the full time series that we have. Okay, so our first regression just comes directly really from proposition 1 that I told you, which is we'll regress the change in a log price in an industry on the industry's network exposure to the commodity times the change in the commodity price. We'll also include a general equilibrium, wage control object as suggested by the model, and finally a time fixed effect. So we'll focus on the cross section here, and really the variation is saying, okay, if you have one sector that has a 10% network exposure and another with a 1% network exposure, do you perceive or do you in the data see additional pass-through in the sectors with higher degrees of network exposure? Okay, and then the key change that we'll make to make the point that pass-through is gradual is that we'll first run this for month-over-month differences, and then we'll do this for year-over-year differences. And if pricing is fully flexible and there's full pass-through in the network model, it shouldn't matter what horizon we use, and we should find beta equals 1 in both cases. So first, I want to show you the month-over-month results. So in column 1, you can see the result if we use oil price changes. And there you get a number of 50% of long-run pass-through happening within 1 month. That number seems quite high, quite fast relative to what I told you at the beginning of the talk. So the first point I want to mention is that that large number seems to be driven particularly by the inclusion of petroleum refineries in the sample. They're a major outlier, both with respect to pass-through speed and their exposure to the commodity. And so if we simply drop that one observation from the regression, or I should say the whole time series associated with refineries, that number drops to 25%. In column 4, we have the same specification, but using these OPEC surprises, identifying the change in the oil price, and we see a similar number, 26%. And then if we look for commodity price changes, if we look at commodity price changes outside of oil, we find still a number of about 34% on impact of the shock. Now, the simple change I'm making and going from this slide to the next slide is now I'm just running this for year-over-year differences rather than month-over-month differences. And you can see in column 2 that 25% number going up to 64% under Kanzig, the Kanzig instrument, all the way up to 76%, and for non-oil commodities all the way up to 74%. So this is why we want to focus on explaining, why is this pass-through so much larger, closer to 1 at a 1-year horizon than a 1-month horizon. And now I want to test explicitly in the 1-month change regression. I want to run heterogeneity analysis on sectors' frequencies of price adjustment and their downstreamness from the shock. And the reason I want to include both of these jointly is that it turns out sectors very downstream from oil tend to have very low frequencies of price adjustment. And so if I didn't include both of these terms together, you might just say, well, I'm telling you downstream sectors price through the shock more slowly, but they just change prices less. Here in columns 4, 5, and 6, we're saying, okay, control for the fact that downstream sectors set prices less frequently than upstream sectors. It still is the case that more downstream sectors pass through the shock more slowly, as implied by the model. Okay, so what I've shown you in this reduced form section is that pass-through is gradual, and even more so for downstream firms. Now we'll turn to whether the model's dynamics can fit the dynamics in the data. Okay, so remember at the bottom of this slide, this is the regression we started with. We had a sector's network exposure to the commodity times the change in the commodity price. We can instead use the dynamics from the Calvo model to decompose that long-run exposure into how much you should be passing through the shock in every moment in time. And so we break down that long-run pass-through into horizon-specific components. And then we multiply those horizon-specific components by the oil price change or the commodity price change that happened at that horizon. So we'll run a very similar regression to before. It's just now the model is telling us how much each sector should pass through a shock that occurs today versus 1 month ago versus 2 months ago, and scaling those by those relevant shocks. And just as before, we should have that beta H equals 1 for all H if the model is correct. Okay. And so the only other point I want to make is that we had to calibrate firms' discount rates. So how forward-looking were they in the solution of the model that we use to test the pass-through speed in the model? And so what we can do to estimate delta is just compare what are the pass-through implications in the model versus what are the pass-through implications that we see in the data. And so I want to show you an example of that now for oil. So in the panel on the right, I'm showing you the model's predicted pass-through of an oil price shock for the average industry. And then I'm overlaying that with our empirical tested pass-through parameters when we use the model evaluated at rational expectations. And so there's a couple points I want to make. First is that the model didn't mechanically have the ability to fit the data, and it fits the data quite well. And so it seems like the empirical pass-through in the data is actually quite slow and in line with those numbers I told you at the beginning, that you have 60% of long-run pass-through in a year, 80% after 2 years. And then finally, the evidence for rational expectations is statistically significant. So the GMM estimate tells us that if we try to fit the model to the data using complete myopia, you don't get nearly as good of a match. Okay. So now I want to move to, that was just thinking about the average industry. What about the cross section? So in the right panel, I'm showing a bin scatter plot using that reduced form result I showed you at the beginning, where we just have a coefficient of 25% on what the flexible model predicts 1 month pass-through to be relative to what actual 1 month price changes are in the data. In the right figure, now I've used the Calvo model for what predicted 1 month price changes should be against actual price changes in the data. We have a coefficient much closer to 1 and an R squared that's about an order of magnitude higher. Now, if we go into year-over-year price changes, it's a similar story. In the flexible pricing model, we only had a pass-through coefficient of 64%, whereas what the Calvo model predicts over 1 year is much closer to what we actually see in the data. The other point I want to point out here in the case of oil is that you actually can explain 8.5% of the variation in all of the PPI data using industry's dynamic exposures to oil price changes, both today and in prior periods. So that's similar to the R squared you'd get from a time fixed effect, for example. Okay, now I mentioned I'd tell you about forward-lookingness in other contexts. So if we look outside of oil, instead of estimating rational expectations, which would be 1, we actually estimate complete myopia for every other commodity that we found in the data. So what this means is that pass-through is already slower, let's say in a Calvo model, than it would be under a menu cost model. And what we're telling you is that outside of oil, pass-through is actually even slower than what a Calvo model with rational expectations would tell you. You need something else to fit what's going on in the data. And so again, if I go for the GMM fit for non-oil commodities, this is using complete myopia. You can see again, we match the pass-through patterns well. Now, finally, in the couple of minutes I have remaining, I want to move to actually this application to aggregate inflation. So I've characterized how commodity price movements kind of dynamically lead to this fanning out of relative prices throughout the economy. Now we want to focus on oil price changes alone. And all I'm going to do is take the personal consumption expenditure weighted average of all of the implied industry effects in the model to put those effects in the unit of aggregate PCE inflation. And then I'll regress actual core inflation on these predictions for how inflation should change. And again, core inflation is this series which is supposedly purged of the components of oil price movements. But if we use what the model predicts for how much indirect oil inflation, which is to say oil making industry prices more expensive outside of just gasoline, you retain a lot of predictive power for core inflation with an R squared about 14% from that analysis. And I should mention that most of this R squared is actually not coming from oil prices in the month of impact. It's coming from lagged oil prices, meaning that the vast majority of this R squared is actually forecast R squared 1 month in advance. Okay, so to conclude, long-run pass-through seems to be given by an industry's network exposure to a shock, not just the industry's direct exposure. Pass-through is more gradual for downstream firms, even holding constant the fact that they pass through, that they set prices less frequently. Firms pass through oil shocks in accord with rational expectations, but act much more myopically for shocks to other commodities. And then finally, the supply chain component of oil inflation is gradual and explains why core inflation is predicted by oil prices. So thank you very much.